Now, if you want to go ahead and get your Chapter 3 notes and print off, you don't need to print off all the pages, but print off the first page of Chapter 3's notes. You can do that. Because we won't get past probably the first page today. Yes, I saw a hand. Okay. If you printed them all out, that's okay, because I don't think it's that many.
It's like 6 pages.
Yeah. Chapter 3's notes are shorter than the other pages.
Oh, yeah, but I guess it's fine.
There. Maybe. And you always include the units that those variables were measured in as part of your axis title. And you always want to have a chart title. That explains what the data is actually showing you. Okay? Your frequencies, the height of each bar tells you how many were in that class. So in this first class, we had 4 bears. In this class here, we had 9 bears. And right up above that in your notes, This is very important. I want you to make a note of it. Because those are test and/or quiz questions. I guarantee you will see those questions on a test or on a quiz. The sum of the class frequencies will always equal the number of data values. Okay? That's also referred to as the sample size. And that has a symbol of N. The sum of the relative frequencies will always equal one or 100%. So the answers to those two questions, you should commit those to memory. You need to know that. I guarantee you will see those questions. Okay? And I don't remember if we answered these last time, so we're going to go ahead and look at them now and make sure that you got them correct at this point. Oh, wrong way. So the class boundaries for our frequency distribution, starting back here with our table, our first class went from 36 to 43. That class actually met with the next class at 43.5. That was the class boundary. And then the upper class boundary for the next class met halfway between 51 and 52. So that was 51.5. And for the next one, it was halfway between 59 and 60, which would have been 59.5. And then these two classes came together at 67.5, halfway between 67 and 68. And if you notice here, the lower class boundary is always 0.5 less than the lower class limit. And the upper class boundary is that same value. It's 0.5 more than the upper class limit. And for that reason, then, we know that the highest class boundary is 0.5 more than 75, and that makes it 75.5. And we also know that the lowest class boundary is 0.5 between the first lower class limit, so that makes it 35.5, 0.5 less than 36. So your class boundaries for our set of data would have been 35.5, 43.5, 51.5, 59.5, 67.5, and 75.5. And if you remember that our class width was 8, what you should also notice here is that this is 8 units apart, as is this, and this, and this, and this. They're all 8 units apart. So this is the boundaries for the first class. This is the boundaries for the second class. This is the boundaries for the third class. This is the boundaries for the fourth class, and this is the boundaries for the last class, the fifth class, or the fifth bar. The boundaries are just where the bars come together, and then where the highest bar leaves off and where the lowest bar begins. Okay? It's like your border lines. So at this point, we should be ready to move on and discuss some common ideas about classes, or about histograms. such as, how do we classify the shape of histograms? And it's a little bit counterintuitive unless we pay attention to the idea that I think I brought up last time, but if I didn't, I'm going to bring it up now. If this was a mountain, and it was covered in snow, and you are a skier, and you got to come down one side of the mountain or the other. Which side of that mountain do you want to come down? You want to come down this side? What's going to happen at the bottom of this side? You crash or you face plant right into the snow. If you're lucky, you don't get skewered by a pine tree. Okay? So if you were going to ski down that slope, you want to ski down this side, right? So the words ski and skew tell you which side that you're going to go down the slope. That slope is skewed left. It's skewed toward the lower numbers. Okay? Because you'd want to ski down the left side, not the right side. Now we're going to look at some others and classify them the same way. So here we've got some more histograms. Let's look at these top two. This histogram is what we would refer to as uniform. The first one is uniform. Your bars are representing your frequencies. So in a uniform distribution, all your bars are about the same height, or nearly so. That doesn't mean that this histogram wouldn't still be uniform if, for example, this bar was a little taller, and this one was a little taller, and this one was a little taller, and maybe this one was a little taller. They're still all relatively the same height. There's not a lot of difference in their heights. The heights or the frequencies don't differ by more than one or maybe two, one way or the other. They're all pretty much the same. Okay? The next one is a histogram that we call bimodal. That means it has two peaks. And this is two distinct peaks. It has two bars that, compared to the bars closest to it, are taller than the ones closest to it. So this bar is taller than either one of the ones on the other side. And this bar is taller than either one of the bars on each other side. So it has two distinct peaks. And those two peaks tell you where the most frequent values are. So unlike the one that's down here below it on the right, which also has a peak, That one has a single peak in the middle. And the most frequent category would be in this bar right here. Then this bar is called symmetrical. Can't spell. Or bell-shaped. And later on in chapter 6, we will refer to this as approximately normal. And the word normal means symmetrical and bell-shaped. Okay? Its highest peak is in the middle, and on both sides of that highest peak, it slopes down on both sides to very, very small numbers of data values. Okay? So the largest count is in the middle. The other two, unlike the symmetrical one, it has a peak. It does have a distinct peak. But this one's peak shows us that it's skewed to the right, because remember, the skew is the side you want to ski down. So it's skewed right. This one, on the other hand, is skewed left, because the peak that causes the gradual increase is on the left. So this one is skewed left. Okay? It isn't the peak that tells you where the skew is. The skew goes the way the skier wants to go off of the peak. Okay? Now, not all distributions are going to fit one of those four categories. All of the others, if they don't fit one of these four categories, we have one catch-all category that we use for all of them. And our catch-all category is asymmetrical or non-symmetrical. Okay? That just means its bars are just all over the place. They're like waves. Okay, there's no clear pattern to them. It doesn't have one tall peak on any place. It doesn't have two distinct peaks. Everything just kind of meanders around. It's all different heights, all different frequencies. Okay, it doesn't start low, end high. It doesn't start high, end low. It doesn't start low, go high in the middle, and then end low. It doesn't stay the same. It just doesn't have a distinctive shape that we can describe it, so we just lump all of those into something that we call asymmetrical. There are some other charts. The histogram we spent a lot of time doing. You saw that it took a whole class period just to do a couple of those. But we're going to make some others that are easy to make by hand. The ones that we're going to make by hand today are stem and leaf plots, time series graphs, dot plots, Pareto charts, and pie charts. The first thing we're going to make is a stem and leaf plot, and the stem and leaf plot that we're going to make is for the point spreads, the points scored by the Ducks football team in the 2014 football team season. And I'm going to tell you right now up front, I did not make up this example. I am not a Ducks fan. I never heard of the Ducks before I saw this problem. But apparently they're a football team. My knowledge of football team is I know who won the Super Bowl yesterday. And I was actually kind of glad to see the Patriots get beat because, I mean, they've been there for a while. And as far as following football, I either root for Notre Dame or whoever's playing against UT. which is not a popular stance, so nobody talks to me about football. Okay? But we're talking about football scores here, and this is the 2014 regular season. And we just look at these numbers, and despite the fact that we don't have that many scores, it's still, we already know that our brain isn't wired to look at a bunch of numbers and be able to talk about what's going on with those numbers. We do better with pictures, or at least something pictured or kind of summarized. So what we're going to do is we're going to make a stem and leaf plot. And when we make it, we need a title, just like we did before. And our title in this case is going to be Points Scored by the Ducks per Game in 2014. So we want a title that gives us information about what the data is that's being shown. Okay? We also want what's called the stem and leaf legend. And what that means is if I have a 4 and a 5, this is the stem and this is the leaf, and that represents the data value 45. And these are not hard to create. We can create these, especially with a really small data set, by simply looking and saying, okay, what's the worst the Ducks did in any one game? 24. Okay, that tells me my first stem needs to start with 2, because it was in the 20s. And it was, in fact, 24. Then I look and say, okay, what's the best they ever did in any game? And I see that was 62. So I need 20s, 30s, 40s, 50s, and 60s. And that one I've already taken care of because I went ahead and gave that my first and last stem. Okay? And that was the only 60s category score they had, I think. So then the rest of them are going to fit in some of these other stems. So this 46 belongs here. And the 48 also belongs there. But the 38 belongs with the 30s. And the 42 belongs with the 40s. And the 45 belongs with the 40s. The 59 belongs with the 50s. The 45 goes up there with the other 45. The 51 belongs down here with the 59. The 44 goes here with the other 40s. And so does the 47. And then the 51 comes down there with the other 51. That is an appropriately labeled stem and leaf plot. Important things to notice here. Do not leave out any of the stems, even if that stem has no leaves. If they had made 38, if that 38 had been a 48, we would have still had to include the 30 stem, and then we would have had 48 here. But we had a 38, so we put it in there. You can't leave out the 30s, even if the 30s have no values that go with it. You have to keep that stem. You can't have any empty or missing stems. They have to all be included because that's part of your spacing. Everything has to be evenly spaced. Okay? Now the good thing about a stem and leaf plot is that if I turn it up sideways, I have a good idea of how the scores are distributed. And I see that the majority of their scores are in the 40s. And that this distribution is in fact approximately normal or approximately bell-shaped, because it has one category that stands high above all the others. In other words, I have what looks like a nice quick histogram. Okay? And this was much less trouble to make than having to come up with class limits and counting all the data values and then drawing a histogram. Actually, I just listed all the data values out and I got the histogram. That happens as long as when you make your stems, you keep in all the stems, even if one of them doesn't have any leaves, and you keep your leaves evenly spaced. And that's a data analysis technique that's used by a lot of researchers that are taking data out in the field. Maybe at the end of the day, they're going to kind of look at just that day's data. Even though they're going to keep collecting, they're going to look at what they had just that day. And this is easy enough to draw with a pen and piece of paper on a clipboard. It's not hard to draw. So they would gain the insight that they would have gained from analyzing a lot of data and having to create a frequency table. They don't even have to do this here. They've got a small data set and it's quick and easy to construct without having to actually start making class limits and drawing graphs. This is an easy graph to construct. Now the good thing here is that it looks like a histogram. It gives us the same information as a histogram, but unlike a histogram, the histogram won't let us recover the data. All we know is that we had 4 bears that weighed around 39.5 and 2 bears that weighed around 47.5 pounds, or that had lengths of about that, okay? Here we actually can recover the data. You can recover the actual data from the stem and leaf. I know I had 24, 38, 46, 48, 42, and so forth. So I could actually write down my data again, even if I didn't have my data table. Even if I wadded it up and threw it away, if I've still got this, I can write down the actual data. So that's a good thing about stem and leaf plots. Stem and leaf plots are one of the favorite things to make. Now another kind of graph, here's my not favorite team. Another kind of graph is a time series graph. So this is going to be a time series graph. In a time series graph or a time series chart, what we're doing is we're going to put the AP poll preseason rankings for the years 2002 through 2007. So that's actually going to be our horizontal axis. So in a time series plot, time is your horizontal axis. And in this particular problem, or set of data, our vertical axis is not counts. Our vertical axis in this case is the ranks. And one thing to think about here is, I had somebody ask me a question this morning, why did I put the lowest rankings at the bottom and the highest rankings at the top? Well, the reason we do that is because conventionally when you draw a graph, 0 is where your horizontal and vertical axes cross. So above your horizontal axis means that the ranking is going up. Now, intuitively in football, which is better, their ranking of 14 or their ranking of number 3? Number 3. That means they're third in the league. So all that means is you have to be careful when you read this chart. When you read this chart, their rankings that are toward the bottom are their best rankings. And then the rankings that are higher up on the chart are their worst rankings. Okay? But that doesn't change the fact that you want to keep your rankings in numerical order starting from the bottom. So in this case, my rankings have to go from a low of 3 to a high of 23. So if this was 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. If I do it that way, I'm barely going to have enough to be able to do this. So if I start this at 0, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Their 23rd ranking is going to be up there a little bit off the chart. So 21's right there, and this is 23. Okay? Now what I do here is I look at how many years I've got, and I'm going from 2002 to 2007, so I need 5 years. So it's okay if I say that this is 2000. And here's 2002. Now, let's see, I don't want to make them quite that close, so I'm just going to leave that off. This is going to be 2002. This is going to be 2003. This is going to be 2004 and 5 and 6 and 7. And I've left time that if I gather some more data, I could continue my rankings. Now, the key here wasn't what this is and what this is. It's the fact that I kept these all 3 blocks apart. 3 blocks basically represents 1 year. So you want to keep those, again, equally spaced. That's very important when you make these charts. So in 2002, their ranking was number 5. And in 2003, they dropped to number 12. Even though my point goes up, that was not as good a ranking. And then their ranking in 2014 dropped, or 2004 dropped even further. But back in 2005 again, they were ranked number 3. Then in 2006, they really dropped all the way to 23. And then their ranking, at least it got better from there. It went back to 15. And then all you do to make this into what's called a time series chart is you connect up the dots. from one year to the next. So from 2002 to 2003, ranking changed to 12. And then they dropped another 2 places in ranking in 2004 to 14. But then in 2005, they achieved their best ranking for that whole period. They were ranked 3rd. And then immediately dropped all the way to the 23rd place the next year, before they came back in 2007 to 15th place. And I don't know where they were in 2008, 9, 10, because the data that I had was only going that far. So although it's counterintuitive to somebody that knows football, as long as you know how football works, you know that this is, okay, they had a decent season, but they didn't do so well for the next 2 years. Then they ranked 3rd before they jumped off the cliff. But they did start coming back. Okay? Now, intuitively, this graph would make more sense if we actually read it, I agree with you, upside down and flipped backwards. But that is a time series chart. It's the actual data values. You make the interpretation of what was going on based on what the data is. Okay? So that's a time series chart, and the thing to remember about time series is your time is always on the x-axis, and depending on what it is, it might be days, minutes, hours. In our case, time was being measured in years. It's very, very important, as you've seen in these examples so far, that you really need to label your axis. You need to label your axes. I think we should give it another shot. I think we should break up. Okay? And she can show it. She can prove it. Because here's the relationship. According to her, the relationship is doing what? Going downhill. And then he's like, maybe you're right. And she says, I knew my data would convince you. And he said, well, no, it's not her data that convinced him. He's convinced because he could do better than someone that doesn't label the axes. Because he doesn't know what she's measuring. She didn't tell him what was going down. Was this like the number of dates or the number of times that he held her hand? You know, she didn't tell him what was going down. So he had no idea, and if she can't tell him what's wrong, then he's like, okay, fine, we'll break up. I'll find somebody else that labels their axes. Our next one is ages of students in Math 1530. And again, you know, we just look at those numbers, we don't see much. So what we need is, we can analyze, and it'll give us a way to kind of do this a little bit better. If we analyze this and say, okay, who's the youngest person in that group? What's the age of the youngest person in that group? That's the 18-year-old. Now, when this line was drawn, apparently somebody didn't anticipate too well, because if you draw this and you label these all by ones, this line's not long enough. Because if I start with 18, what I want to do with a dot plot is I want to label every single possible age. So that means in this particular case, I'm going to have to go 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, because the oldest person in the group is 42. Okay? Now, I could have counted each one of those tick marks as 2 years and gone 18, 20, 22, 24, and it would have been okay. It would have just been a little crowded when I start making my dots. Usually, I don't make you have one of these. I'll usually let you draw your own and scale it the way you want to. So in this case, my 18-year-olds, what you do is each one of these 18-year-olds is going to be a dot. So this first 18-year-old is a dot. And the 19-year-old is a dot. And the 20-year-old is a dot. This other 18-year-old is another dot, but it's on the 18 mark. The 35-year-old is a dot over 35. The 26-year-old is a dot over 26. The 18-year-old goes back in the 18-year-old group. Then 21, 20, 24, 38, 18, 24, 21, 22, 18, 19, 42, 27, 26, and 19. How far are those dots spread from one another? Is there a lot of variability in the ages of the students in that class? Yeah, because the oldest one's all the way up here, and then we got a couple more that are kind of outside of where everybody else is. The majority of the students actually are the students down that way. So this is a skewed very, very, very right distribution. Okay? It's a very skewed right distribution. Because there's a few on the higher end, but not many. Now, one of the things that we're actually going to do in the next section, and this is not actually on your handout at this time, but I'm going to go ahead and show you another chart that is easily constructed with a small data set by hand. It actually doesn't come up until chapter 3. But when we construct this chart, what I'm going to do is I'm going to actually take this data and I'm going to sort it out. I've already found the maximum and the minimum age. The minimum age was 18 and the maximum age was 42. And I know that I have 1, 2, 3, 4, 5 times 4 is 20 students. And they're represented by those 20 dots. What I would like to find next is what is the age of the middle of those 20 students when I put them in order, from youngest to oldest. So since I have 20 students, divided by 2 is 10, so my middle student is going to be the age of the 10th plus the 11th student divided by 2 because I've got 10 younger students and 10 older students. Okay? That's the 50-50 point. And I can count and see where the 10th and 11th students are. Because here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th student is 20. And the 11th student is 21. So the middle of the 10th and the 11th students' ages is 20.5. And that's called the median. We're going to talk about that in chapter 3. And notice, I'm not doing a lot of math here. All I'm doing really is counting. I didn't actually have to add 20 and 21. I know that halfway between 20 and 21 is 20.5. I also want to know the middle of the younger students. What's the middle age of the youngest 50% of the students? That's actually called the first quartile, or the 25th percentile. So if I look only at the 10 youngest students, my 10 youngest are down here. And my oldest ones are to the right of that orange line that I just drew. So there's 10 students here, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students that are in the older group. The middle of my younger group would be, let's see, the 10th student. If I take 10 divided by 2, I get 5, so it's between the 5th and the 6th student. So here's 1, 2, 3, 4, 5, and then the 6th student is 19. So that means my first quartile or 25th percentile, the middle of my bottom half, is 18.5. And then the middle of my upper half, or what's called my third quartile, which is the same as the 75th percentile, is going to be the middle of those 10 older students. And again, that's going to be between the 5th and the 6th. So here's 1, 2, 3, 4, 5, 6. So for these two students, there are 1, 2, 3, 4 older, and 1, 2, 3, 4 older than the upper one. So 4 younger, 4 older. And halfway between 24 and 26 is 25. What I just constructed, without needing a calculator or doing too much math, what I've just constructed there is called the 5-number summary. And it tells me that half of my students are between 18 and 20.5. Half of them are between 20.5 and 42. 25% of them are between 18.5 and 20.5. And 25% of them are between 20.5 and 25. And I can make other judgments based on that too. But the good thing about the 5-number summary is it leads us to something called a box and whisker plot. Which shows us something similar to what this does. But it only looks at these 5 numbers. So if I were to make a box and whisker plot of this data, and I'm going to use the same axis that I used here, then I would make a mark at my minimum data value, which is 18. One at my 25th percentile, which is 18 and a half. One at the median, which is 20 and a half. One at my 75th percentile, or the middle of my upper students, my older students, which would be 25. And then I'd make a mark at the oldest student. The box connects up the quartiles. The whiskers connects the box to the minimum and the maximum. And looking at that box and whisker plot, it's really, really obvious to me, both by the dot plot and by the length of that upper whisker, that that data set is skewed right. It's easy to see that the data set is skewed right. Because the right whisker on the box plot is even longer than the width of the box plot, which is where 50% of my students' ages are. So it's like almost 3 times as much as the width of that box. Okay? The width of that box goes from 18 and a half to 25. Which is 6.5 units wide. And from 25 to 42, is 17 units. So this is more than twice the value of the distance between my two quartiles. That tells me that whisker is like 2.5 times as long as the span for the middle 50%. Very much skewed right. Those are the kind of things that we want to be able to tell people. We can tell people most of the students in this probability and statistics class were between 18 and about 20 years old. More than half of the students were between 18 and 21. They did have one 42-year-old that could have been an outlier, and that's the point here. The 42-year-old student is an outlier. And there could be a number of reasons for that 42-year-old student being where they are. They could be in that class. We have students that are in their 40s and 50s in our classes with our 18 and 20-year-old students, because there's lots of people that come to college. There's no market just for the 18 to 20-year-olds. We have lots of people that come to get more education. The other thing to keep in mind is whoever was collecting this data might accidentally have written down this age backwards. That student might not have been 42, they may have actually been 24, and they made a mistake in data. Okay, that could be a possibility. But that still leaves the fact that the 38-year-old is pretty much out there too. And I don't think they had an 83-year-old that they wrote that one down backwards. So you don't throw out the outliers, you just be aware of what happens with the outliers. And by the end of class today, we're going to see that when you have outlier data, that it affects your numerical statistics a lot. The outlier doesn't have to be on the upper end. We could have had a lot of older people and maybe 1 or 2 younger people, and the younger people would have been the outlier. So outlier simply means it's at the extremes and it's far away from most of the other data values. Okay, we'll talk a lot about outliers. We're going to do example 6, And example 6 isn't hard to make. It's actually easier to make since we've already got the frequency chart. It's easier to make than the histogram. The only hitch here, we're not going to make what's called a bar chart. If we made a bar chart, it would look a lot like what we're going to make, except the bars would have been listed by van, sports car, sedan, motorcycle, and truck, because that's the way they came in the table. We're going to turn the bar chart into what's called a Pareto chart. And a Pareto chart is a bar chart where the bars are arranged from tallest to shortest. That's the important difference. They're arranged. The tallest bar comes first and the shortest one comes last. So since we're making a bar chart that is arranged from tallest, our tallest is going to be this one. It's going to come first because it has the highest frequency. And that frequency is 19, so I need to make this axis so that I can show where 19 is. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've only got 10 chunks. Maybe the best way to do that is to label this by 2, so that this would be 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Because I can go halfway between two of those to get the odd numbers. So here's my sedans. They're going to go up to 19. So I have a bar, and that bar represents the sedans. My next highest category is the people that bought trucks. I don't want these to touch. I want to leave a gap. So my trucks are going to be here. And that goes up to 12. So I can see how my trucks sold in proportion to how the sedans sold. Then my next category in order of frequency is the vans. And again, I'm going to leave a gap, and it's going to be the same distance gap, the same width. And it only goes up to 8. And then the next category is going to be the sports cars with a frequency of 6. And then the last one is going to be the motorcycles. And it only goes up to 2. So that's called a Pareto chart. The bars are in order. Just like my other charts, I need to label the axes and label the chart. The chart's title is Best-selling vehicles, because these were sold at an auction. And the best-selling vehicles you can see easily are the sedans and the trucks. My horizontal axis type is be nice if I could spell. Vehicle type. My vertical axis number of vehicles sold, completely labeled. Bar chart, which happens to be a Pareto chart because the bars are in order. So key things to remember here. Your bars are equal width. Gaps between the bars are equal width. And since it's a Pareto chart, the bars are in order, tallest to shortest. I am going to tell you, today is the only day that you'll ever have to make any of these by hand except for your homework assignment. Okay? We are going to use Excel, which is lots faster than this. I'm actually going to show y'all how to make this, and then we're going to take a break. We're going to come back and do one more really short topic, and then we'll be done for the day, and we'll come back on Wednesday and finish up with chapter 3. This one is hard to make by hand. I'm going to convince you here that Excel is your friend, because Excel can make this in the time it takes me to type in this chart. It's going to take us a little bit longer, but the reason I'm going to go through it is to make sure you understand what actually is going on with a pie chart. We're going to make a pie chart of this. And you got a circle labeled by degrees to go along to make your pie chart on. So I'm going to show you how to make this if you needed to by hand. We have to do a little arithmetic first. We need a calculator to do the arithmetic. I don't do this stuff in my head. I don't expect you to either. So I'm going to grab the calculator. And the first thing I'm going to do is I'm going to total up how many bags of chips this vendor actually sold. And this vendor sold 338 bags of chips. He sold 62 barbecue chips, and the proportion would be 62 divided by 338. But I'm going to turn that into a decimal. So that's about 0.183. Now I'm actually going to keep all those decimals, but I just rounded it off with the proportion. There are 360 degrees in the circle. So I'm going to multiply 360 times that decimal. And I got 66, and I'm going to round it off to whole degrees. So I got 66 degrees. Okay? Now, does everybody see how I know that it's 66 degrees?
That one you don't round up.
No, that one's 66.03 would round kind of in the irregular thing. The only thing you ever have to round up is class width. That's the only thing. Okay? Just class width. So this is 66 degrees, and I'm going to go ahead and mark the first segment of the circle so you can see why I do it the way that I do it. So I need to mark off 66 degrees for my barbecue chips. So I'm going to start at 0 degrees, which is right here. And I'm going to go up to 66 degrees, is just a little more than halfway between 60 and 70 degrees. And I'm going to make sure it's dark enough that you can actually see my segment. So that part of the circle represents my barbecue chips. And it is actually 0.183 or 18.3% of sales was barbecue chips. Okay? So I have my first segment. Now I go back to my table, and the next segment is going to have 118 bags out of 338. Which is about 34.9%. So I'm going to multiply that times 360. And I'm going to call that 126 degrees. So I need a segment that joins onto the one I just finished but goes another 126 degrees. So I need to go, starting here, I need to go 126 degrees that way. And the only way that I can do that is to add that to the degrees I just had. I had 66 degrees plus an additional 126 puts me at the 192 degree mark. So here's 190. There's 192. So that's why I went there. So what that tells me is this whole big segment this big chunk here, remember, was about 34.9, almost 35% of the circle. And that, if you look, it makes sense. That's about 35% of the circle. That's a little better than a third of the circle. This was plain chips. That's your plain chips. And it was 34.9% of the sales. And there's my next segment. Then I go back to the table. Sour cream and onion, they sold 45 bags. So 45 divided by 338 is about 13.3%. And we'll call that 48 degrees. Plus 47.9, we'll round up pretty closely to about 48. So that means I'm going to take my 126 degrees and I need to go another 48 degrees. So if I take 48 degrees plus the 192 that I'm at now, that puts me at 240 degrees. And this segment represents the sour cream and onion. And their share of the sales was about about 13.3%. Then I have salt and vinegar. Salt and vinegar, they only sold 29 bags of those. That's a shame because I would have bought 29 bags probably myself. I like those. But 29 divided by 338 is about 8.6%. Which is about 31 degrees. So if I tack on another 31 degrees, I'm at 271 degrees. So this is salt and vinegar, and it is about 8.6%. And that means since we only have one category left, that's the cheddar cheese. And there's 84 bags of those sold. That's not quite 25%. And that's about, we'll call that 89 degrees, although it's pretty close to 90. And if I go from where I was on the circle, I get 359, or actually, because of round off error, I'm back to 360 degrees. So that tells me my cheddar is what it's supposed to be. That's just a check. So at this point, I know that that whole segment, which represents 24.9% of all the sales, was the cheddar chips. Now, I think you'd agree with me that's a pretty tedious process to make what is really a very simple to read chart, but it's a lot of work. So the point here is, aren't you glad most of those can be made in Excel? The ones Excel doesn't make, dot plots, stem plots, it does not make those. But those are usually charts you make with pencil and paper, and you don't have more than about 25 pieces of data, so it's not a real tedious thing to do by hand. Things like this are hard to do. Histograms are annoying at best. You have to come up with your own frequency distribution. Excel can go ahead and turn that into a histogram for you and nothing flat. Same thing with bar charts and Pareto charts. Now, I'm going to give you about a 10-minute break to kind of clear your head. We're going to come back. We're going to do the very first problem on chapter 3, and that's it. And the reason I'm going ahead with it is because it is mostly concepts you already know. There's only one new one. And we've already talked about outliers, so we're going to talk about outliers some more. So we're going to begin chapter 3. And we're going to talk about something called measures of center. Now, there's two words that I want you to associate with measures of center. One of them is expected value. And that gets the idea that if I told you to envision a classroom full of Math 1530 students, what do you think their age is, or what do you think a typical student in that class, what age would they be? You would tell me what age you would expect a Math 1530 college student to be, right? Normally, the expected value is what we think would be usual. If we have to pin it down to one number, it's the usual value, which we think of as the expected value. That's the statistical term. A typical value and the most often used one is the word average. what do you think the age of the average college student is? Now, the problem with that word average is what your mind already thinks it is. Because there are 4 different measures of average. But when I say the word average to you, what do you think? What do you think you do when you get an average? That's exactly right. You add them all up and divide by the number that you have. That actually has a meaning, and it's called a mean. You add up all the values and divide by the number of values. And actually, when we come to writing this down as a formula, adding up all the values, we use the symbol capital sigma, which means add up all the numbers. And the values we'll refer to as x, and the number of values is our sample size, and we usually refer to that as n. Okay? So the way we calculate the mean is we add up the x's and divide by n. How many x's did you have? Okay? That's not the only measure of average, and in fact it has some drawbacks. Probably the easiest measure of average is the mode. The mode simply looks at which value occurs most often, which value has the highest count. Highest count or frequency. And then there's another pretty good one called the median. We actually looked at that already. The median is the middle of a rank ordered set of data. You're finding the middle value, but you have to put them in order from low to high first. Okay? If you have an odd number of data values, there will be one single middle value. Like if you have 15 pieces of data, the middle value is the 8th piece of data. Because there's 7 that are less than the 8th piece, and there's 7 that are more than the 8th piece. Okay? If you have an even number of data values, then it will be between the 2 that are in the middle. So like in the example we looked at, we had 20 pieces of data. The median was between the 10th and the 11th. Because that's where the dividing line was. There is one more that you've probably never heard of. And that's called the mid-range. And I'm going to be honest with you, even as a statistician, a trained statistician, I never heard of the mid-range until I started teaching statistics, and only in the last few years have I heard about a mid-range. Because a mid-range isn't something statisticians use. And you're going to see why we don't use it, even though there's a lot of people that will use a mid-range, but they use it to mislead you. So we're gonna see why the mid-range, while it is actually sort of, I guess you can define it as a measure of center, it's not a very good one, it's not a very useful one. Because the mid-range is the number halfway between the minimum and the maximum. And that can be a problem. So what we're going to do is, for the data set we see right here, we're going to calculate all of the measures of center. The first one we're going to calculate is going to be the mean. And the way that we're going to calculate the mean is we're going to take 500 plus 840 plus 470 plus 480 plus 420 plus 440 twice, and we're going to divide by 1, 2, 3, 4, 5, 6, 7 numbers. And we're going to use a calculator because we are not going to do all this in our head. So that comes out to be 3590 over 7. And we're going to round to 1 decimal place. We need 1 decimal place more than what our data is, and our data is whole numbers. And that comes out to be 512.85, which we'll call 512.9. Okay? That's the most work you're going to do. The others are going to be much simpler to do, because most of them are based on count or a little subtraction problem. So, the median. To do the median, we need to arrange the numbers first in order. The smallest number is 420, followed by 440 twice, then 470, then 480, then 500, and then 840. So there's 1, 2, 3, 4, 5, 6, 7 data values, and I think you can see that the middle one is 470. Okay. The mode, we don't even have to rearrange, although we can see it quickly here, or we can see it here. Since there's only 7 numbers, it's easy to pick out the fact that 440 shows up twice. And that's because there's 2 of them. It's the mode because there's 2. Everything else shows up once. Then we come to the mid-range. The mid-range compares only the lowest and the highest and tries to see what's dead center between those two. The mid-range is 630. Now, before we go on and do anything else, we're looking to find a value, since we're talking about a sample of 10,000 BTU room air conditioners that we're going to buy. And the measures of center, we have all 4 of them. We're looking for what we expect to pay for a 10,000 BTU air conditioner, based upon the data that we're looking at. Which of these measures do you think is the best measure of what you expect to pay? $512, $470, $440, or $630? Which one do you think is the best? Okay, we get a vote for the mode, the 440. And that's not bad because it's within the distance that we're looking at. And even if we rank order it, it shows up more than once, so maybe the mode would be the best. It would be a fairly good guess. Why would you not want to pick the mean? Nobody jumped up and said, oh, we're going to use the mean, because that's usually what everybody wants. They look at average and they think, okay, that's the mean. Why is the mean not our best guess for what we're going to have to pay for an air conditioner?
So it's way more than the other 10.
That's right. It's more than all but one of the sample prices. Okay? It's way too high. It's way more. Would you ever expect to pay $630? No, there's only one air conditioner that costs more than $630, and that's that 841. So unless you want the Cadillac of air conditioners, why would you buy that? Okay? What's the problem with this number and this number, where these are both pretty reasonable estimates of what we would have to pay? What made those so much higher? The 840, I mean, you look at it pretty clearly. You can see, you know, it goes 400s, 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 500. Okay, it was close to the 400s. $840? Where did that come from? Okay, that's not expected at all. So here's the thing. What we would want to do then to actually calculate this, and it doesn't take long, I'm going to show you that it doesn't take long at all, is we're going to leave out that 840. And I'm actually going to write the numbers on the other sheet, but we're going to work from the sheet we already have. Because we can be done in about 1 minute if we work from there. If I leave out that $840, what that does is it makes that $35.90 $840 less. And it keeps me now dividing by 6 air conditioners. That's $458. That's a big difference. If I leave out the $840 when I'm calculating the median, I don't have 7 numbers anymore, I have 6. And the middle 2 numbers are 440 and 470. And the median is now 460. And I don't need the calculator, so I'm going to get rid of it. So now the median is 460. $2 difference in the median and the mean. If I leave out the 840, does the mode change? Nope. So your choice of the mode was a good choice too. 440, 460, 458. All good ballpark answers. The only one, if I leave out that 440, that now makes this 500. And 500 plus 420 is 920, and the middle of that is 4... I think I did this one wrong, 910, 450. That's 455, sorry. This is the one that's 460, because half of 920 is 460. So if I leave out the outlier, the mean drops to 458. The median drops to 455. The mode drops to, well, it didn't drop to anything. It stayed the same. And the mid-range, as lousy a measure as it was, now is a lot more ballpark with what the best measure of center is, which is around 455, 460. Okay? So outliers cause you grief. Can you just throw them away? No, because it's an actual data value, and I'll explain as we go along. There's a lot of cases where outliers, because they did throw them away, created a really bad situation. But you need to be aware that they're there. You need to know that they're there and acknowledge their presence. Okay? See you on Wednesday. Y'all have a good evening. It's right here. Back there. There's usually a stapler in every room we've got. The question is where it actually is.